Brilliant. Well, welcome back to the last bit of day two. And so now we're moving on to the next bit of the earthquake cycle, not the earthquake post-seismic bit, but the interseismic, the bit between earthquakes. And the strain that builds up in the crust accumulates over time and is ultimately released, typically in earthquakes. So the applications of INSAR, we went over the earthquakes themselves, deformation patterns you see, and now we'll focus on the strain bending of the crust that you observe over decadal timescales between earthquakes. But with the other aspects of the earthquake cycle I mentioned, post-seismic, so understanding the rheology, depth, extent, process of the vast slip versus viscoelastic relaxation. That's something you can do. Volcanoes we'll get tomorrow. Landslide, near surface process, glaciers, doing quite a bit on land substance due to water extraction, and then if you're interested in the noise, tropospheric water vapor fields as well. So many applications of INSAR, we're just going to focus on the second bit now. And the reason we want to do that is to get an understanding of earthquakes, the forces that are building up, the pressures, the strain that builds up to earthquakes, how they're going to be released on these active faults, and then the potential for seismic hazard, and consequently the risk if it's near urban population centres. So we don't just want to look at the earthquake, the effect, we want to look at how that builds up, where, and how fast, and then as a consequence, how that seismic hazard is distributed. Is it localized on faults? Is it quite distributed across? And then understanding an earth process, how do the continents deform? That's the question. And for the continents onshore, GPS and INSAR are really good ways of measuring these small things. By small, an earthquake measuring was about a meter slip, gave you a few tens of centimeters of displacement in a few seconds, and you're measuring that in the interferogram. Here we're trying to measure not meters or tens of centimeters, we're trying to measure millimeters in a year. So it's a very small amount across quite a long time. Not an instantaneous, but an accumulated displacement of just a few millimeters. And we want to do that at the size of at least the UK. So something big, over a long wavelengths, not over small sort of areas that you might do if you're doing, say, landslide or embankment stability or something like that. And we're trying to understand the properties of the upper crust and how it builds up and supports these kind of earthquakes. So let's return back to our Turkey example, North Anatolian fault, big strike slip faults across Northern Anatolia. Looking again, we're now looking at that build-up of strain. And there's no slip at the surface, all the slip is occurring on a fault shear zone at depth due to the far-field forces of the plates. So we did the earthquake, we've done that bit. We're not doing the post-seismic deformation, but we are looking at this long-term accumulation of strain. Now, we assume it's constant rate, just for simplicity. It won't be. And we assume nothing's moving, but there are parts of the fault system that do creep and do give offsets. They're all complications to it. But it's the same thing. We want to look at the short-term hazard, long-term, looking at the role of faulting and growth of mountains. So let's take a toy example. Here's this big scale we're looking at, looking down on the earth and a fault. And we build a fence across that fault, hundreds of kilometers long. And far-field tectonic forces are moving these blocks, these plates relative to each other. And over time, they might move 5 meters over a very long time. It gives you this warping, that's strain. Something that's been bent, it's accumulated strain, there's strain energy in that. And it just accumulates that over time, maybe constant, maybe not. But if you've ever built a fence that long and waited that many hundreds of years, it would look like that. Then you build a new fence, one day, a nice straight fence. Then in the earthquake, suddenly it releases that strain, bend, and snaps it back. So you get a finite offset. That's what you measured earlier, the cosine offset. And this is what you then see is that recovery. It's that bend that I showed in North Anatolia. You go into the field and you see a fence and you measure that offset. But if you just built the fence, it shows you that recovery of that strain. And that tends to happen over hundreds of years. The earthquake itself happens in just seconds. And that's the earthquake cycle. So here's an actual example of after the earthquake, the Darfield one, that New Zealand example, a fence that was straight before the earthquake that's been offset. So a completely different scale. This is not over 100 kilometers. This is just a few tens, but that records how much the fault has slipped at the surface. And then here's an example from Turkey again, where that rock has gone through here, offset the fences. And if it's in the near field, obviously buildings right on it are going to struggle to withstand both finite offset and the shaping in the near field. And that's why you get collapse of these buildings and a large number of fatalities from them. So what we try and do, and colleagues in the past have done this here, the Interseismic Deformation, is to look at that slow accumulation of millimeters per year over country scales, if we can do it, to hundreds of kilometers between earthquakes, and build up a map that says, this basically says, this is moving 30 millimeters that way relative to something that's moving to 10 millimeters that way. So it's trying to build up that picture of the shear that occurs at these boundaries. And it's important for understanding the earthquake cycle. How does that then relate to the large scale deformation of whole plate areas? We would want to look at the spatial variation of fault parameters along here. Do they all accumulate strain in the same way? Does it tell you anything different about deeper rheology here? Can you get anything from that? And then the distribution of seismic hazard, is it what we call locked and building up strain by cities like Istanbul that are hit by earthquakes every couple of hundreds of years? And as I said earlier, we want to try and use that, not the earthquakes themselves, not looking after the event, but trying to look before. One way is this GPS compilation of Corning's framework over a decade ago, looking at the strain rate. Hot colours, it's building up pressure fast, so the subduction zones are the main areas that do this. That's why you get big earthquakes there, they're fast, big plate boundaries. But as I said, across the continent, it's really quite distributed. Some areas blue, not deforming much, some areas yellow, quite a bit of deformation, but they're not straight lines. There are some straight lines here, but it's quite broad and distributed across this. So what I want to do is relate where the strain's happening and then ultimately where that's released in earthquakes. Because if they map one to one, you've got a starting point. You're working by hypothesis is you need to build up strain to then release it in earthquakes. Does it map very well? And if you look at certain areas, this is eastern Turkey, where we're measuring strain, how fast it builds up, maps quite closely to where it's ultimately released in those earthquakes. So either how often the earthquakes happen or how much energy is released. Same in California, areas in blue not building up tend to not have many earthquakes, whereas those that are San Andreas, for instance, building up have more. And we want to do this for societal reasons, not just the science of doing it, and that's the seismic hazard, the potential for shaking, and the risk, the potential for causing disasters because populations are exposed to it. So one metric of doing that is to look at, say, 50 capitals here. They're all located in deforming parts of the region, places that are building up that pressure. And that build-up of strain is the hazard. These cities are there, so they're exposed. That's your exposure, the people and the buildings that are on those bits of the crust that have that hazard. And often, if they're in low-income countries, the building types may not be seismically resistant, so they have an increased vulnerability. So that convolution, is there a hazard there? Are there any people there? And the buildings they're in, are they fragile? Are they going to fall down due to the shaking, the vulnerability of the system? So one measure of that is strain rate. You say this is more hazardous, this is more exposure, and then the red colour is more vulnerable. So you can then start to pick out the kind of cities like Port-au-Prince I showed you. It's very vulnerable, very exposed, very high hazard, and that's why you get big earthquakes that kill hundreds of thousands of people. So one way is to target these kinds of cities, to focus your energies on the ones that would maximise your return. But that's how you there get that risk from that convolution of those properties. So as I showed you before, we were looking at the earthquake impact with the co-seismic, much more with this now. We're in the interseismic here, trying to look at the preparedness for area, trying to mark out which regions are building up strain, how fast, how big an area, how localized, and to do that within SAR, focusing on the SDGs, sort of sustainable cities and communities, those urban infrastructures. And it's sort of all being able to do this has only really been possible in the last 20 years, because you're trying to measure that from a satellite 700 kilometers up over a very long way for some of the size of the country. So this was work that was done that could measure that across the North Anatolian, the very early work, compared to GPS when there wasn't much GPS about. And you're trying to get these profiles across the fault. You expect to get this kind of shape, that's that strain, that bending, that elastic band kind of shape. And you can build that up into map view, not just profiles across the fault, but a map view to get that. Now this is the early data. It's hard to get these kind of measurements, but it's possible to do it in Turkey. It's possible to do it in California, where there was good coherence and you could sort of measure it. So that idea, that concept that these faults, they're not slipping at the surface, but that deep shear zone is moving. That deep shear zone that moves causes a warping of the Earth's crust. That was shown to be possible to recover with INSAR over quite large areas. It's possible to see it before with GPS, but the GPS is so sparse, it didn't give you quite such a complete picture. So one of the questions is, why is that strain accumulated around the faults? Well, I've hinted at it. It's something to do with going deep on in the Earth. The other cost is what we call LOX. It's not moving in the interseismic period. Eventually, you're going to get an offset, showing an offset fence. But you have a far field velocity. There's always some plate motion, relative motion. So if they get a load of GPS or a load of INSAR, what you're trying to measure is that far field motion. So in the far field, you've got the displacement relative to some reference point. That far field is moving at some velocity v. So that will accumulate over time. Then in the near field, you've got that recovery of that velocity. On average, the bit in the middle is going to half that velocity, and all the earthquakes are going to return that elastic strain energy. And you also get some of that post-seismic effect, that non-linear effect. So here's where the earthquakes happen. They happen in the seismogenic crust. I mentioned earlier that's about 15 kilometers, 20, depending on the heat structure of the crust. And the interseismic stuff's going on down here in the shear zone. And the post-seismic viscoelastic is also happening down here, that part of the earthquake cycle. Where we're trying to look at the spatial pattern, the deformation, that wavelength you did in the post-seismic, that tells you about the thickness of this. So the space, the amplitude in space tells you about the earthquake, the seismogenic, and then how that pattern decays the post-seismic, that time dependence is geology. And if the interseismic is constant, we can start to look at the stress-strain relationships for that. So what we'll do today, though, is just the simplest analytical model for that build-up of strain, and that's the screw dislocation, which has this simple arctan that gives you this almost sigmoidal pattern. It's an arctan function pattern across. Very simple, but it's been quite effective at explaining single strike slip faults. So if you want to just focus on the simplest ones, and we say we've got that upper locked warp bit, offset at depth, and you just try and fit a couple of parameters. It's nice because it's only a 2-parameter model. It tells you how much is the ground moving relative to some reference, depends on how fast it's slipping, about millimeters per year, and how thick that LOX layer is deep. The thicker it is, the longer the wavelength signal. So it's a bit like the co-seismic. And we want to be able to do that. To get those parameters, we're just basically doing a fitting exercise. So it should be a lot simpler than the earthquake ones at first. And the way we view that is to think of dislocations, like in lattice theory, that there is a screw dislocation in the Earth. It gives you that warping because you get that offset. It's sort of synonymous with that kind of view lattice work, with that kind of thing. That's an analogy for the faults. There's an edge dislocation that's a bit more like dikes. We might do that tomorrow. But for this, we call it a screw dislocation model. And as I said, it's very simple, but when we did a compilation a while ago, it's quite effective. We found over 100 studies, almost 200 studies where that actually worked quite well. And they were able to, different authors around the world for different faults were able to estimate a locking depth as well as an offset. And then what we found was that where you get the co-seismic here, so the values that are in black here, about 12 kilometers, the interseismic is roughly the same within uncertainty. That basically where the LOX lid is not moving in the interseismic is ultimately how thick the seismogenic layer is, how big the earthquake rupture will be for the sort of big earthquakes that break through the whole crust. So it tends to be about 15 kilometers. It depends where you are in the world. So we picked up different areas of the world where we estimated where those, show the map again. Yeah, we all around, these are faults all around the world, and then we get seismogenic thicknesses mainly less than 20 kilometers. So it's not a large fraction, well, it's not all of the crust, not all of the continental crust, that maybe 35 kilometers, maybe 70 kilometers. In Tibet, for instance, it's less than that. Now, one thing is a bit like the earthquakes. There's a problem that you're measuring information at the surface. Your data is just a surface observation about motion at depth. So we've got this same problem that any of this surface motion is you're trying to measure slip down here. There's a sort of ability to resolve it that it's indistinguishable from a load of motion separated out here. So if it's near surface, you can resolve it really well. But when you're down here, you can't tell whether it's a single shear zone or we call it distributed shear zone. So there's still that issue resolving. So if you have lots of closely spaced faults, it will be not possible to resolve all their shear zones. You'll get a sort of step series of arctan functions to them. The other thing we want to address is what do we measure today? Has it any bearing on what's measured in the past, geology? So what we measure with InSight geology, that rate, is it meaningful for the really long term? Because we're only measuring over about 10 years, decadal timescale. Is it the same as an offset over 10,000 years for Holocene dated offsets? Is it the same over 1,000,000 years for geological offsets? Is that what we get? And at times it felt like there was a bit of a discrepancy, but on the whole, it seems to be quite good agreement for a lot of areas that the geodetic rates are roughly what the geological slip rates are. They're not out by an order of magnitude, they're not out by many factors. And then there is some subtle interesting differences that you would want to look at the biology of the faults. And the relaxation either might tell you there are some differences. But you can see that sort of uncertainty on these measurements is quite large. So you can't, it gets hard to tell if they significantly do disagree. We need to get better at measuring some of these, both through better data and better modeling. So the key take home from that is interseismic strain is localized around these faults, particularly strike slip faults. It's a bit different for dip slip faults. We can use a simple dislocation model in the first instance to try and model it to get at how fast is it moving, the slip rate, and how deep is that locking depth and where that shear zone may be. And using InSight and GNSS, it is possible to get down to the sort of millimeter per year level. If you work really hard, have lots of data, remove a lot of the noise, it is possible to get a couple of millimeters per year, but it's very difficult. So if you're looking at faults that you've dated geologically, they're only moving a millimeter per year, you probably wouldn't see them geodetically. It's at the limit of what we. Generally, the rates we measure today are a good guide to the past with some caveats. And we find that, we haven't covered it here, but there is rapid post-seismic that you image after earthquakes. So you've got to account for the earthquake, what happens in the days, weeks, and months after the earthquake, the post-seismic, and then ask, are you back to the long-term interseismic? There is some debate about the time-varying behavior of that strain accumulation. So we ignored any, we've treated it as a screw dislocation, so just a plane offset. We don't account for any finite width for the shear zone. We don't look at different spatial variations and elastic properties. You can complicate the model a bit and say one side's more rigid than the other, and that gives you an asymmetry in that arctan strain. We don't look at any temporal variations for the earthquake cycle. We just say it's constant at the moment. And we don't look at any spatial variations in slip rate. So you can imagine a bit like the earthquake, you can look at how the slip changes along strike, not just treat it as a uniform slip. You can look at it varying. You could do the same with the locking depth. So you either portion your data up across hundreds of kilometers and ask, does the slip vary along strike? And you can do more complex variations in fault locking and creep. So that idea that it's not always locked, but if there's a seismic slip going on at the near surface, a sort of creeping mechanism that isn't earthquake generating, but still releases some of that strain, then that complicates the model a bit as well. So I'll give you just some examples from that North Anatolian fault where the early measurements were made 20 years ago. So this example, and how that's built up over time. This is from a friend and colleague of mine when he worked on this area. So it went from small bits of the fault to expanding that and looking at it from two different directions, covering both the North and East Anatolian fault. So over 10 years, the amount of data we could work with built up. You can still sort of see the noise band is about a couple of millimeters per year. In this case, it's still difficult, but there's more GPS to have as an independent verification of what we're measuring. But we're definitely seeing that strain accumulating across faults. And then another colleague here in the past, Ekbar Hussain, then did it more systematically over wide areas and introduced this group. The difference here is instead of having that arctan function, that sort of sigmoidal shape, you actually have an offset step, a bit like the earthquake. It's a silent earthquake, it's creep, so it gives you that sharp offset. If you saw it at the surface, it would be an offset of a few millimeters per year. So what he did was to systematically build up all that data all along strike on the descending. So we're looking west, and on the ascending east to build up a sort of more complete picture of it. And it was done over longer time frames. That's 2003 to 2010 with the EMPHASAT. So prior to Sentinel, that was our main satellite to use. And he used a small baseline approach to do that for his time series. He improved the unwrapping. The unwrapping is often quite a difficult step where you get a lot of errors. It doesn't matter quite so much for the earthquakes when you're measuring tens of centimeters. It matters a lot, the unwrapping errors, when you do millimeters per year. And this was a sort of uncertainty, just getting a few millimeters per year. But there was a increasing, as I say, more and more GPS, that's the red vectors here, are telling you the story as well. So if you have GPS everywhere, which is starting to get to in Turkey and is definitely true in Europe, the INSAR contributes less information. In areas that are sparse with GPS, and the INSAR contributes quite a lot of new information. And you do it in this practical, you can combine all that data, the ascending, the descending, and the GPS velocities to resolve them into an east-west. So we said the satellite can't see east-west, it has a contribution from the east-west, but it doesn't see it, it sees in its line of sight. But if you know enough information, you can resolve the east-west and the vertical. You're not very sensitive to the north, you can't measure very precisely, but for this kind of strike slip fault that's east-west is actually where most of the motion is happening. So you get east-west, and then vertical doesn't tend to have anything to do with tectonics. It's got stuff to do with anthropogenic, hydrological sort of impacts, water substance, water extraction, land subsiding, other motions, landslides on a small scale. It's hard to measure tectonic. We've been able to measure in New Zealand about a centimetre per year of actual uplift, tectonic uplift. But in most places, it's either noise or it's something else. And then that got to the stage, the next iteration was to do that for the whole country. So now you can actually start to see, this is the east velocity, you can actually see the plate motion. There's a strong contrast here, and then the whole block's moving east. So Anatolia is relatively rigid, but not completely rigid. And there's eastward motion relative to Eurasia. So I'm trying to understand. And then the vertical gain is all water substance down here. There's nothing particularly systematic as the few millimeters per year. But we're seeing those same sort of shapes across the faults. And the reason we want to get the velocities is to understand the kinematics of the problem, how do the plates deform. But we also want to look at that strain rate, because that then leads on to the localization of hazard. Where is it building up that pressure? Where's the strain? So as I said, when you come to where you've got a lot of GNSS, you get a fairly good idea. GNSS is our velocity measurements. They tell you where the pressure is building up because there's a large gradient in the velocity. So that's along here. But you can see that by putting in the inside, it sort of refines that a bit. It localizes the strain more. You get a bit more information than you did before. And that tells you where that shear strain, where that motion is happening. So you can, if you want, go and look on our portal. All the interferogram data is there. So you've got LIGSPAS for the time series, the interferogram. There are codes available then to look at the strain rate, but you could work with that kind of data. To do it at scale is quite an endeavor, but you could also do it for individual faults if you wanted to. But that data is free. We've got on ascending and descending directions. And you could do a similar sort of analysis to this, and you'll do a bit in the practical. So as I say, you're trying to get the slip rate, how fast is the fault moving, and how thick is that locking depth. The thicker it is, the bigger the area that might rupture in an earthquake. So it's a sort of first order control on how big an earthquake could be. So what we want you to do is solve for that slip rate. So that simple arc-time function, you want to solve for S, the slip rate, D, that locking depth. There are other complications you have to account for the rotation of the plates, but we won't need to do that here. But you can, if you carry on to the Jupyter notebook, start to include that creep, the near surface aseismic slip of the fault. It's not locked. It releases some fraction, some potential of that strain. So then you get a sharp discomfort. Then you're going for slip rate, locking depth, but also other parameters, the creep rate, and what depth range that creeps are carrying on. So remember, fault tends to be locked over 15 kilometers, but you could get some near surface creep of a few kilometers. So that's best seen in schematic view here. Here's your North Anatolian fault zone. Here's that dislocation, screw dislocation, idealized view of a shear zone at depth. This is locked, not moving, it's building up strain. But for some reason, that strain build-up, the stress concentration causes it to slip. It might be walls of fluids, it might be something to do with the actual fault gouge, its fault friction properties that mean it doesn't sustain that stress, so it freely slides at some fraction of the overall slip rate. So here you've got a slip rate of 20 millimeters per year. It gives you that red line. And then the creep releases some of it, the green line. And the green line is like an earthquake shape, but it's aseismic. It doesn't generate the seismic waves, but it gives you that sort of shape. So if you take those away from each other, you get the black line. And that's the kind of shape. So if you get the black line shape, you know there's some creep involved. If you get the red line shape, it's just interseismic strain accumulation. And as I said, you can do that systematically and break your data up along the strike of a fault and see where it's creeping in the west and where it's accumulating strain in the east and how fast it is and how that may relate to the unzipping of the North Atlantic fault and the propagation of earthquakes in the past. Depends what scientific questions you're trying to answer with it. So the final iteration of that was, in the past we were doing it at countrywide scales. We've done Turkey, we've done Iran, we've done the expensive plateau. Each part of the research group were working on different aspects of it. It's sort of culminated now in trying to do this really at a continental scale. So now you're trying to understand why all these red faults are distributed across Eurasia as a result of the plates colliding with it, and what's that strain over really quite large distances. So we've just finished this work. So Jin's at the back has been working on this. He'll be leading the practical this afternoon, but it's a big endeavour now covering not just Turkey, but we've applied this across the whole Eurasian deforming zone, the Alpine Himalayan belt. So here we've got the two line of sights from the Sentinel, and those can then be combined to resolve the strains. So in white, not much strain building up. These are relatively aseismic regions, and then in black, large build-up of strain. So North Anatolian fault camp comes out as it did before. It was a similar set of data. And other parts of the world, premieres, large strikes, spots have had earthquakes in Tibetan Plateau. That's your sort of pressure map. A bit like that global one I showed you from the GNSS. It's just a bit higher resolution now for the continents. And we can also look at different parts of that strain rate. Another one is dilatation. This tells you in green, it's where you're pulling apart the crust and it's thinning, it's collapsing. So Greece does that, Turkey does that, and Tibet does that bit, but you can see it's a lot noisier. So it's still really quite hard. We're measuring nano strain per year. That millimeters per year over 100 kilometers is a nano strain per year. And it's tough to do it. Yeah. In the continents doesn't quite deform as fast as you think. And then here we've got the vorticity, so it tells you which bits are shearing and rotating in the system as well. And again, it picks out nicely where the faults are, and it also picks out nicely where it's a bit noisy. So it gives us some marker of the noise. So that's the end of the Interseismic bit. We'll go on to practical. Any questions about that Interseismic? Was quite a quick one on that. No. So for the practical, yes.
So how good does it work in like the educated area?
Yes, good question. It is the bane of our life because it works well in Iran. It's nice and coherent. So in Afghanistan, we get good results. In vegetated areas in Northern Europe, it really, we tried to improve it here, but it's not great. And you can't do it down here in India. You can see where it really breaks down, where it's very vegetated in the Ganges. So C-band won't work for this. We're waiting for NISAR, L-band. ALOS does not have enough data. You need massive data. You need petabytes of data to do this. So you don't get that from most systems. You only get that from Sentinel, really, to be able to get these very small strain rates. So yeah, we're just hopeful that it will work in those vegetated, because that's where some of the biggest strain actually is here, and then along the Sagan fault. That's where we are. Yes.
Do we have like a knowledge of the uncertainties in the strain rates? Does that matter?
Yes, yeah, we can get the uncertainties and the velocities that then you propagate through. So one measure of uncertainty is like the noise floor here where nothing's happening. So you can do the formal uncertainty to say it wouldn't be many nanostrain when you propagate it through. But realistically, you're going to see the noise floor is about 10 to 20 nanostrain, where it should be 0. You can see that modeling. So that would be roughly what I'd say is. We use the GPS to constrain the INSAR, so they're not independent. But you sort of get an idea that it's quite a few millimeters to see a discrepancy with the velocity data. So when you're working at this and the east-west up down, the velocities there is a discrepancy of many millimeters per year. So we have to do a lot of sort of averaging and fitting to sort of make it work. So we can't. This is high resolution that you get from the GPS, but not as much as you'd expect given the radar data is 100 meters, because the noise is correlated. 100 meters to the next is highly correlated noise. They're not independent, so you can't measure strains over short wavelength. You can only do it over relatively long wavelength. So for the practical, Jin's going to just lead you through that. It's this data fitting exercise with 2 parameters. How fast, how deep, and then he'll build up the complexity. So you're looking for this arctan function across a fault. So plates are moving, faults here, locked and loaded, ready to break in an earthquake, but between the earthquakes it's pulling out that pressure. And it's a data fitting exercise. How does the shape change? Remember, amplitude matters, like for the earthquakes, and depth, how deep it is, affects the wavelength at which you see it. So you're just looking for changing those parameters and getting a fit. So D for the depth, locking depth, S for the slip rate. But Jin will go over that now. And I think that's exactly half past. So should we just go straight into it?
A couple of questions online.
Yeah, yeah, do the live set up. Yeah, for the Q&A. Sorry, yeah. You're doing it off the laptop. Yeah, so for mainly these all centre around, we only focus on strike slip earthquakes because they're simple to do with that screw dislocation. You can do bat slip calculations for subduction zones and follow that approach. It works at big scales and subduction zones because they're over large areas. If you're looking at distributed small dip slip faults, say across Anatolia, all those normal faults or across the Bear, it's not so clear how good that strain shows up as localized on the faults. But yeah, there are modeling approaches to do it, but they're usually called backslip calculations to do it, where you basically run it like an earthquake and then subtract the difference to get at what the interseismic should be for a thrust fault, say, where you were getting a lot of convergence as possible. I think they're mainly about that.
Oh, yes.
So the method is merging the multipath data set. So this is what Jin does to do some cold bell maps. You take the INSAR line of sight, you use the GNSS, you sort of get, because INSAR is always relative, not in an absolute reference frame, so it's trying to relatively tie them together and adjust them for long wave errors. So it's something called bell map, which is available on GitHub as well. And that allows piece of code to tie all those data sets together. Okay, that's a good question. Yeah, so this is one of our big issues. Afghanistan, the Herat earthquakes happen in a region of low strain. And it's becoming increasingly clear that even if you've got low strain at the level we can measure it, 10 nanostrains per year, that's still high enough to have earthquakes. It's just the earthquake rate, the size of the earthquakes will be lower, but it doesn't mean you would have no earthquakes. In a similar way that in the middle of Australia, right to the side of the interior plate, you still get small earthquakes. The New Madrid zone in North America had a huge earthquake, but you wouldn't expect it very often. So very low strain doesn't mean the total absence of earthquakes, it just means the earthquake rate is likely to be lower. Right, I better let you go on, carry on.
Okay. Can people online hear me and see the screen? Okay. It's been a long day, but we're nearly there. Just one more session to go. Hope everyone has enjoyed the workshop so far. And let's wrap up today with the Interseismic practical. So I guess I'm going to skip these slides because John has got these covered in the background. So let's dive straight into the practical. We noticed some issues with the workshop link, so let's stick with the binder. If you just type this link into your browser and launch the binder there. It's also a QR code for the link. And for those joining online, I'll drop this in the chat in case you haven't got access to.
You put it in the Q&A.
It's in the Q&A.
Yes, in the top. Q&A.
That's more questions. That one. Q&A. Okay, so let's click the first link to launch the practical notebook. Everyone has got the binder launched now, or anyone having issues? Okay, now let's click this button here to show the whole notebook. And let's first import the required models. You can just press Shift plus Enter. Follow with me. Follow along with me. And in this practical, we're going to analyze data from Tibet. In our GIL paper published in last year, specifically there are one ascending and one descending data that covers the Xianxuhe fault. And LixBus results for all these frames have been archived on Zenodo. So first, to get a feel for how the model behaves, we are going to start by generating some synthetic velocities using screw dislocation model. For example, let's set slip rate and lock-in depth of 20 millimeters per year and 20 kilometers respectively. And we'll compare with a reference solution, say 10 millimeters per year and 10 kilometers depth. We can plot the results. So on the left plot, you can see a simple 1D screw dislocation model, and on the right, we expanded the model to 2D, assuming the fault strikes roughly from west to east. Well, these fault parallel velocities are what we want for modeling fault slip. They're not what we directly measure with INSA. Remember, SAR satellites, for example, Sentinel one look down at the ground with the incidence angle roughly of about 31 to 46 degrees, and it varies across the scene. And more importantly, INSA can only measure displacement towards or away from the sunlight. That's the line of sight component. So let's go ahead and apply a line of sight projection to our signals and see what effect this has on the velocities. So what we can see here is first the signal magnitude decreases compared to the east-west parallel velocities, and there is a slight change across the scene. For example, from near range to far range. So it varies across the satellite track because the incidence angle is not a constant. Now we've seen how a screw dislocation model looks in INSA. Now we can move on to applying the model to real world data. So let's first load our next pass outputs, and then we'll plot the two velocity from these two Lexa frames, and the red line shows the central fault. By default, Lexa sets motion towards the satellite as positive, and the motion away from the satellite as negative. And these velocities are related to a Lexa selected reference point within each frame. We can see a change in the line of sight velocities across the fault. But remember, what we want is fault parallel velocities, but ours are currently in the satellite line of sight. To get what we need, we'll need to decompose our line of sight velocities into three components: fault parallel, fault perpendicular, and vertical velocities. The challenge here is that we got three unknowns, but only two data sets, one ascending and one descending. So to make progress, we need to, for example, assume the fault perpendicular displacement is zero, because we expect the dominant motion of the central fault to be strike slip motion, meaning the motion is primarily along the strike with minimal fault perpendicular movement. So now we've got two data sets, one ascending and descending, but these are on two slightly different grids, and we need to unify the grids so that we can perform the velocity decomposition for shared points. So yeah, now we are regrading the velocities onto a new grid so that they will share the overlapped region points. And now another important thing to know is that the two velocity fields are relative to their own reference pixels, and we need to make sure they share the same reference so that the velocities can be decomposed correctly. And we're going to define a reference window here away from the major deformation and use the mean velocities within that area as the reference. as shown here as a black rectangle. And then we run the decomposition for each pixel, assuming no correlation between pixels, and a fourth strike of 130 degrees. So, as expected, we can only get the decomposed velocities in the overlap area, where we have both line of sight to work with. And so we are now take profile across the fault to produce data set. We can apply our screw dislocation model. First, we need to project our longitude latitude coordinates into UTM so that the distance are in millimeters, in meters, and not degrees. So let's take a profile across perpendicular to the fault, like this way. The vertical dashed line marks where the profile intersects with the central fault. And we also include the intersection angle here. We want this to be 90 degrees. Otherwise, the signals will become smeared and affect our results. So, well, these profiled velocities are a little noisy, but you still see an overall change in velocity across the fault with a shape that's similar to an arctangent function that we discussed earlier. So now we've got our data ready. Let's produce a simple forward model to get an idea of what model parameters produce a reasonable fit. So let's start with an initial guess. And as you can see, this first attempt gives quite a poor fit to the data. The idea here is to experiment. You can adjust these parameters to get a better match between the model and the observed velocity profile. A quick reminder about what each parameter does is that the velocity step across the fault controls slip rate, and a velocity gradient across the fault reflects the locking depth. A steeper gradient means shallower locking depth. For example, if you slightly shift the model curve slightly downwards a bit, downwards, for example, and reduce the slip rate a bit. And also make the locking depth shallower. We're starting to get a better alignment with the observed profile. So have a go at tweaking these parameters until you get a model that fits well. And once you're happy with your results, let me know your best answer by filling out this form. Anyone has got a better answer than this misfit? Yeah,
1.6.
1.6. Good. And anyone getting even better? Okay, so now got 8 responses, and the minimum so far is 1.6.
1.5.
1.5. Yeah, that's great. Ah, we've got a 1.4. Even better.
which parameters do you use to get one song?
Anyone getting below 1.4 in the room?
Yeah.
Okay, let's move on. You may have noticed that there is a steep gradient across the fault, meaning that this could be a sign of fault creep, meaning a very shallow locking depth. Now let's move on to the fault creeps section. So fault creep means the fault is slipping seismically at shallow depth up to the surface, and this fault creep occurs alongside the deeper interseismic slip. Now let's look at this profile again, and now we are run the model that includes fault creep parameters. And by adding some creep parameters, again, this is not a good fit for now, so you can have a go at tweaking these parameters, see what combination gives a better fit. And once you are happy with your answer, filling out this form. So we've got more free parameters, including creep rate, creep depth. So we've got three parameters here.
Which one is the grid?
Sorry.
Which one is the grid? C.
S2 is free plate.
D2.
D2, you can take a look at this figure here. C is for grip, D2 is grip depth, S is slip rate, D1 is locking depth. So for the scraping at the rate of C between the surface and the depth D2, and a deeper interseismic slip S occurs below depth D1. Anyone getting better answer? Was the RMS misfit? 1.5. Center has got down to 1.3-ish. Below 1.3. What's the best answer in the room? 1.3. Okay. So what are your parameter combinations with 1.3 RMS misfit?
So just it's a bit unrealistic.
S1,
Now I got 1%, like 5%. Look in there. And I'll return. I'm about it.
1.4. Yeah. What's your answer? S1
minus 0.2. Not so perfect.
minus 0.2.
7 for instance.
7,
18.
18,
It is the same.
18,
11
11,
and minus 10.
minus 7, and 0. Let's have a look. 1.4 to 7. Yeah, looks a reasonable fit. Anyone got a better answer? Right. Can play after the session if you want, because it's kind of manual tweaking. And let's move on to strain rate. So it's actually more useful to look at strain rates because they tell us what's actually deforming. Estimates of strain rate can highlight where deformation is concentrated. Here's the equation we used to calculate strain rate tensor. And in this case, we've got fault parallel velocities, so we can only estimate shear strain across the fault. For our screw dislocation model, we can forward calculate the shear strain using this equation. So now let's start by calculate strain rate for the screw dislocation model that will fit to our profile using both the forward model and by taking the gradient in the model velocities. For example, you'll see there's about a factor of 2 difference between the modeled strain rates and the estimated one. That is because of the difference between engineering strain and tensor strain. So if you'd like to know more details about this, you can take a look at the Jonathan's paper. And so we can get nice smooth estimates of strain rate from our screw dislocation model, but in real studies, we often want to estimate strain rates directly from our velocities. But we still need some degree of smoothing to suppress short wavelength noise in the inside. This noise is small compared to the tectonic signal, but it can cause large gradients between neighboring points and then drown out the underlying tectonic strain rate. So let's plot both. One strain rate directly calculated from the beam profile fault parallel velocities, and one calculated with the same velocities, but with some smoothing with a sliding window average. You can try changing the size of a smoothing window here. So by applying a smoothing window, something like a window size of 5 works well, shown as blue lines. We can bring out higher strain across the fault trace. If we increase the window size too much, we end up smoothing out our original interseismic signal, and this strain peak disappears again. So how we choose to filter out high frequency noise in the velocities is crucial. And in addition to estimating strain rates from profiled velocities, we can also calculate strain rate in 2D from our decomposed fault parallel velocities based on our previous assumption of zero fault perpendicular motion. We can split the fault parallel velocities into northward and eastward components, and then we can take the gradients both in x and y direction. So as with the profile velocities, we'll first need to filter the decomposed fault parallel velocities to remove any short wavelength noise. You can try experimenting with the filter type and width here. For example, a medium filter or a Gaussian filter. Here we apply a medium filter to the decomposed fault parallel velocities. This is the filtered velocities. And we calculate northward and eastward velocities from fault parallel velocities. And then we take the velocity gradients and calculate maximum shear strain. And we plot the shear strain in 2D map. So here we go. We've got this localized strain aligning with the central fault trace, highlighting the area of concentrated deformation. you can either choose a different smoothing type for example, Gaussian, or and a different strength for filter width. Here the width is in degrees. Okay, so far we've done forward calculations to estimate slip rates and lock-in depths, which, as you've seen, is quite a kind of manual tweaking, but we don't want to do this way. Another way to approach this more systematically is through Bayesian inversion. So in geophysics, we can estimate model parameters and their uncertainties from Bayesian inversion. The idea is to combine some prior knowledge about the model with a likelihood function based on the observations, which gives us the posterior probability. We assume uniform priors for each model parameters using these limits, meaning all values between the upper and the lower limits are equally likely. Values outside of these limits are impossible, and they will get rejected during the inversion. So let's run this Bayesian inversion with 10,000 iterations. It might take a couple minutes. So while we're waiting, any questions for now?
Discharge.
Okay, now it's finished. Now let's plot the accepted trial models for sleep rate and lock-in depth to see how the algorithm explores the parameter space. We'll show the first 1% of the iterations in red and the rest in blue. These early iterations are often called a burn-in period, where the inversion is moving from the start position towards the global minimum, and then begins to explore more fully. We can also look at the inversion, how the inversion explored the model parameter space by plotting the likelihood function value for each iteration. So you can see that after the first burn-in period, the weighted residual dropped down quickly. And now let's plot our best model on top of the profile velocities here, like this way, and also with 95% confidence interval. So it's still not a perfect match because we are only searching for three parameters: sleep rate, lock-in depth, and offset. We should need a more accurate functional form for the Bayesian inversion. So this is kind of just a simple example. And now let's plot histograms for each model parameters like this way. So ideally, each histogram should be roughly Gaussian, but sometimes they may be skewed or rough depending on the number of iterations that have been run or the parameter step sizes. And we also plot the red line that should also align with the peak of the histograms, but sometimes the lock-in depth, like here, tends to appear shallower as indicated by the steep velocity gradient. So let's plot. We can also show the distribution of each model parameters against each other, so we can see the correlation or trade-off between each model parameters. Up here, we can see some trade-off, for example, between sleep rate and lock-in depth, or sleep rate between offset as even stronger trade-off.
And the red is the lowest RMS. The red dot.
The red dots are yet the minimum RMS, and the darkest region here shows the most probable solutions, so they don't sometimes match. We can also show just the correlation between sleep rate and lock-in depth, which is usually there is a trade-off between them. If we make sleep rate higher, we need also larger lock-in depth. So far, we've shown by modeling velocity profiles, we can get sleep rates and lock-in depth, but we don't want to take lots of individual profiles, especially with very dense fault networks. So that's where block modeling comes in. In block models, we divide a region into small blocks that are rotate relative to each other. This can be really efficient if we have sparse geodetic data, but it does get challenging with complex fault arrays or where some faults haven't been mapped. For example, here are the block boundaries defined by Richard, and the white lines show places where no mapped faults exist. One of the limitations of the block modeling is that all strain must occur along block boundaries, and each block must be fully enclosed by faults, even if some faults may not actually exist. If we look at the best fit strain predicted by a block model, it doesn't really match what we see in the observations. Some boundaries predict strain that where none is observed. Alternative way is to directly invert strain rates for slip rates. One of the key advantages here is that we don't need to think about the rotation because strains don't contain rotation. And so we don't need to define tectonic blocks or macro plates. So beyond just estimating fault slip rates, we can also solve for off-fault distributed moment sources that can help explain the observed diffuse deformation that is not concentrated on mapped faults. And actually, this does a better job than block modeling at matching the geological slip rates. In block modeling, faults come in freely, so slip rate can only taper off towards the fault tips if strain is transferred onto another fault. But with the new approach, we can capture the realistic tapering of slip rates, which lines up better with what we see in the geology. So we recommend the direct inversion of strain rate as the preferred method, and the code package is listed in the notebook below here if you want to try it out. And I'm happy to take any questions. That's it for the practical. Any questions?
The question about the Bayesian block you just showed. Why do you get the distribution of blocking depth when it's either shallow or deep? And how can you decide which one to just take to?
Yeah, that's a good question. Very often we get a poor estimate for locking depth. Always shift between these parameters, and some studies just fix locking depth to some like seismogenic depth, basic evidence. But sometimes it's hard to tell. We don't know the right answer. But it looks here because we've got a steeper gradient. That means very shallow locking depth. That should be more probable, I would say. Any questions? Are there any questions online or in the room?
I was going to suggest that the inversion model is that easy to add further parameters like breed. So you can add further, so it just notice on the log like VXI and C, but can you include further parameters on that easily enough? So
You mean Bayesian inversion?
the inversion model.
Yeah, we can add more free parameters and explore it more systematically. Yeah, here we only search for 3 parameters, but you can search for more, like creeping grip rate, grip depth. You need to hack the code a bit. All questions online? Nope. Good. So I think that's it for the